I wish they would have used parentheses because it's not exactly clear. I think they're referring to the S sub I greater than T. So I think it's these states which are distributed according to policy function. Can you see? Am I right there? This I greater than T is the subscript of the S. The tilde is following the S, I believe. Now, don't just take my word as the foremost authority on it. I didn't read this paper. You might read it and find out I'm just wrong. But I'm trying to help you parse this. So I think what we're saying here is the states are distributed according to the policy. In other words, the policy is deciding what you're going to do, right? And so, isn't it actions would be distributed according to the policy? I've misread. States are distributed according to E. Actions are distributed according to the policy because the policy says what actions you're going to do. Okay, what the heck is E? It's your environment. Okay, when you write a paper, don't use the letter E to mean environment if you've also used the letter E in a different font to mean expected value in the same dumb equation because blah! Just wanted to get that out.
Also don't use subscripts.
Yeah, and don't use subscripts of subscripts unless we put parentheses in there. But nevertheless, we don't get to rewrite their paper. We get to operate in the world they've created for us. Okay, states are distributed by the environment. That makes sense, right? You could, in this environment, there are a set of states available to you, and so we're going to go according to those. By the way, if you wanted to describe the distributions of things, it's a really great way to make your equations big and complex and hairy and be more explicit without really adding any new information. Just pro tip for when you write your next technical paper. Okay, actions distributed according to your policy. Rewards, given, state, and action. This vertical pipe means given. Do you see that policy of rewards, given, state, and action is kind of saying state and action are the inputs to this probability distribution. Reward is what comes out, I think. Is that R reward? Notice they use R here and R there as well under two different.
Discounted future reward.
That's what it is. R is discounted future reward. How does discounted future reward differ from reward?
Multiplied by gamma.
Yeah, but it's the sum of all the way into the future of multiplying by gamma raised to the power of the time step of the future of all the rewards for all of eternity. So the reward is what you get when you do the one action. I stepped here, I saved the princess, yeah, I get a reward. Discounted future reward means basically how good is it to do this one thing right now? It's the Q value is what discounted future reward really is. It's the how good am I doing thinking about how close I am to my goals and how good everything is in the future and how much I discount them for being far away and all of that stuff. Okay, so really...
The value is the sum of all the discounted future rewards dictated by your policy in your environment.
Yeah, so look what this whole equation is saying. Q value, according to your current policy, given your state and your action, is how much you expect to get in the future, given that you're going to go through the states that exist in the environment in which you're in, and you perform the actions according to the actions you're probably going to do because your policy says to do them, and this is what you'll get on average in the future, given where your state and actions would be. Do you see this is basically Bellman's equation? Okay, so we've taken the time to stare at it. It was a whole lot of symbols just to say Bellman's equation. And they could have just written the word Bellman equation. See Wikipedia article and given the URL, and that would have been really nice, wouldn't it? But they didn't. They composed their own version of Bellman equation. Okay. And they do it again and again to basically show that, hey, look, we understand Q-learning. And we could have gotten all of that from just reading the section headings because, look, this is where they describe their algorithm. All of this is the background section. And in the background section, you expect stuff that everybody already knows. So if you didn't get any of that, you could just have a link to the Wikipedia article on Q-learning here, and that would have been fine. Why should you read this anyway?
So you get practice.
Because they are going to be expressing in their own notation, their own equations right here. And when you look at this and say, bah, I have no idea what they're talking about, that's because you didn't take the time to connect with them. So yes, you understand this stuff, but you need to know how they say it so that when you read their equations for their algorithm, you'll speak their language. Okay, so let's go down here and read their equations for their algorithm. Now, if you'll recall, this is the one that uses, it basically says, hey, we're going to do the actor-critic model. In the actor-critic model, we've got two models, one that is a policy model and one that is the Q-table model, right? Okay. Let's go through this equation. We did last time, but I want to do it again because we didn't do it in excruciating, painful detail. Notice we're computing a gradient here because that's what the upside down triangle means. Why do we compute gradients? It's to update neural networks. Yeah, it means, hey, if we go in this direction, that tells us how changing these parameters, theta, will affect the output of the neural network. So what gradient symbol, when you see that pop up, especially if there's a subscript theta, you know for sure, hey, they're tuning a neural net here. Or some other differentiable model. It could very well be a linear model. It could be any model that you can differentiate, but that's a great way to optimize differentiable models, and so that's what they're doing here is gradient descent. Let's see. The gradient of the weights of mu. Happen to know mu is defined right here. The DPG algorithm maintains a parameterized actor function mu of s of theta mu. So what is mu?
Yeah.
It's the actor. And what is an actor?
It maps from state to action.
Yep, it maps from state to action. In other words, it's the policy. So what they're really saying right here is the gradient of the weights of the policy model. Catch that? Is equal to, or times j. I recall seeing the letter j right here. The goal of reinforcement learning is to learn a policy which maximizes the expected return from the start distribution j, which is the expected reward all the way discounted into the future. So apparently j is the start distribution. Okay? The gradient given the start distribution. Now, why would we only want it for the start distribution?
Isn't it the gradient of the start distribution? And theta and mu are just subscript?
So when we see this gradient, the subscript is what you're differentiating with respect to. Yeah, you're right. It is the gradient of the start distribution. I'm a little unclear on that. Let's come back to that j and see if we can settle on what that means in a minute. For right now, I'm just going to call that fluff and pretend that j doesn't exist. Okay. Now, what does the wiggly equal sign mean? Yeah, not exactly equal to, but approximately equal to the expected value of states distributed according to rho sub beta. Okay. Rho sub beta. I haven't seen that around lately. States are apparently often distributed according to rho sub beta. Rho to the pi. We denote the discounted state visitation distribution for a policy pi as rho to the pi. So apparently rho they're using for discounted state visitation distribution. I think that means how often the agent is going to visit all the states in the state space. And pi is policy. Now we just need to figure out what beta is. Okay, I'm not seeing a beta. Anybody see a beta?
So rho sub pi is what?
It's basically the distribution of how you visit all the states given your policy.
Okay, so
I'm thinking.
Rho sub beta,
Or how much your policy tells you to visit all the states.
well, rho sub beta is just the same thing for different policies.
I think so. Okay, let's put beta and j on our queue of things we still need to figure out. Now notice that we're saying that the gradient here is approximately equal to some gradient. What does that tell you? We're computing a gradient based on a gradient. Does that remind you of anything?
Yeah.
You know how we could keep computing q values based on future q values? Bet you that's what's going on here.
Well,
Is that what you're going to say?
Kind of what they're saying is that okay, the Q table is actually just an approximation to, it tells us how good our actions are, or the value, the utility of taking certain actions in certain states. But there is an actual optimal path, and the Q table is just an approximation to that path. Is that what that approximation could mean?
Could be. That's a very reasonable interpretation in my view. I think I'll leave it at that because I'm not 100% certain and I don't want to mislead you. Okay, there's a difference here I want to point out. Right there, we've got theta to the q, and over here we've got theta mu's. See theta q and you see theta mu? I think that's an important key for penetrating this equation. How do you suppose theta q differs from theta mu?
Weights for different models, the actor and the critical.
Yeah, these are weights for different models, and we know that mu right here is the actor function. So we can say already, hey look, we're talking about the actor right here because we're using mu's, and here we're talking about the critic because we're using q's. Okay. So, what we're suggesting here is that the gradient for the actor depends on the gradient for the critic multiplied by the gradient for the actor. Does that remind you of anything?
Yep, chain rule.
Yeah, do you remember the chain rule? When we take the... Okay, let's draw this picture again. So, don't want to save it, just go away. Okay, we have a model. This model feeds into another model. Okay, and this feeds into some target output, and we compute the target minus predicted. Right? And that makes our loss function. This tells us how bad that neural network is doing. Well, this is the loss function that is the loss function for this model. And then using the chain rule, if we take the gradient of this thing and we multiply by it, we've basically got a loss function for this model. And as it happens, this one is the actor, and this one is the critic. So what I'm pretty sure this is saying right here is, hey look, if we want to update our actor, which is this model this is the harder one to update because this is the one that's underneath, right, that feeds into the critic. The way we do it is we figure out how we update the Q table, and we use the chain rule to continue on and update that one. Okay. Another thing to point out, this notation, mu of S pipe theta. When you see this notation with a vertical pipe, it usually means they're using probability distributions. Do you know what a probability distribution is? You comfortable with them? Okay. Basically, there's usually some finite set of choices, or it could be continuous distribution, but for right now, let's pretend it's finite just because it's easier to reason about. And we'll say, okay.
Read discrete?
Yeah, I meant discrete. So given the weights of this model, there's some distribution of states, and we're going to suggest that this mu represents that probability distribution. So if you think of a distribution as a function, what comes after the pipe is the input, and what comes before the pipe is the output. We're kind of saying how the states are distributed according to the current weights of the actor model. And that's what this mu distribution is.